Okay, so first I would like to thank the organizer for the opportunity to speak in this wonderful conference. And I also would like to thank the audience for staying, just me between you and your lunch. So I'll try to be brief. So in today's talk, it's basically based on a recent preprint I put out with my postdoc, Josh Quails. So over the past few years, we have seen a revival of bootstrap technique applied to the study of conformal field theory. And we have obtained some fantastic results. For example, the bound on the scaling dimension, the operator expansion coefficient, and then more recently applied to the context of holography. And for example, recently I think there was a nice paper proving the conformal collider bound using the idea coming from the conformal bootstrap. And it's fair to say that in all this type of study, conformal block, or more precisely, the availabilities and the properties of a conformal block play the central roles in helping us to obtain those results. So in today's talk, which really based on the work kind of emerges over the past few months, I will try to make an attempt to answer and try to discuss the following question. So the first one is really that, are there more systematic or perhaps unified and even more efficient ways to actually obtain the conformal block in various dimensions and also in various setups? For example, going beyond the usual game of bootstrapping the scalar conformal block, but actually, for example, if you start to look at the things with space-time indices, then story become more complicated. I must mention that there have been various previous wonderful attempts. For example, just name a few, such as a shadow formalism, or recently there's some nice work by Masahiro Yamazaki and collaborator trying to generalize the recurrence relation of a Zamolodchikov. And also, of course, there's a radial expansion. I will review that momentarily. So the new spin of the game here is really trying to understand the underlying integrable structure inside those conformal blocks. And I guess this is a direction now which has been less touched upon in the kind of study of bootstrap community, which are more focused on actually trying to obtaining those various well, for example, scaling dimension or OPE by a numerical method. But I think this story is actually kind of new, but also old, because the lesson we are really trying to draw here is that can we try to generalize the beautiful correspondence which people learn when they study the two-dimensional conformal field theory, basically the correspondence between when you consider the correlation functions with a degenerative vertex operator inserted, and with a various eigenfunction or basically a Hamiltonian in the integrable system. And the question is that can we generalize those things from two-dimensional CFT to higher dimension? This does not seem so crazy, I think, anymore, since recently there are some beautiful work like classifying those known states for the higher dimensional conformal field theory. And once we establish, so basically in today's talk, I'm going to try to at least consider the simplest case, trying to establish those correspondence. And then we'll try to briefly discuss how general those correspondence can be. And eventually, I think we're really trying to cast an eye, trying to understand whether such a correspondence can actually arise from the holographic dual of those conformal field theory. So that's basically the plan of the talk. Okay, so let me start by reviewing some general conformal field theory law in D dimension just to settle the stage. So we will mainly focus on the 4-point correlation functions. And for the simplicity, let's begin with setting all the 4 fields are actually scalar primary. So they are just simply labeled by their scaling dimensions. And as we know that using the conformal symmetry, we can actually fix them into the following general forms, that where the xij are the differences between the different space-time points where those fields are actually inserted, and A and B are the differences between their different scaling dimension. And then ultimately, we fix the whole thing to a yet to be determined function of the so-called conformal cross ratio, which I define usually written in terms of U and V. But here, I also going to introduce a set of complex variable Z and Z bar, which are really complex conjugate, which will be more convenient to use in a later discussion. But we can actually further decompose this 4-point correlation function into the various contributions from different type of exchange operator, which we call the O, and they are labeled by its own scaling dimension and spins. So we basically inserted basically like a projector into this 4-point correlation function and turn these things into a summation. And we decompose what's inside into basically a pair of a 3-point function. And so they are basically associated with those OPE coefficient, which the Shota Komatsu was talking about, kind of calculate those things using the holography. And the W this here is something usually called the conformal partial waves. Okay, so furthermore, the conformal symmetry also allows us to fix those conformal partial wave into the following form. And the G here is basically a star object for today. It's the so-called conformal block. And it's associated with a particular operator exchange, basically O delta L exchange between those field phi 1, 2, 3, 4. And basically, the whole bootstrap game started with, now you consider you have different way to actually decompose those your 4-point correlation function into different conformal partial way. There are different channels you can basically exchange. But those OPE coefficients have to satisfy this crossing symmetry equation, or basically OPE associativity. So when you change the, for example, phi 1 and the phi 3, then when you summing over all the possible exchange channel, even though individual will be different, but when you're summing all of them, they have to be equal to each other. And basically, the ability to actually, and then you can basically try to do it for unitary CFT. So now, if we know the conformal block in some exact, or at least some approximately usable form that you can do it numerically, then you can use a unitarity to assume basically the OPE coefficient to be positive definite, and you can start doing your semi-definite programming and so on, and start putting on all this fantastic bound on the scaling dimension. And you can see those beautiful recent review by Rajkov and Simon Stuffing for the development so far. But we basically need to know them, essentially, in order. Basically, I think that the message here is the knowledge of those conformal block basically determines what we can actually bootstrap with. Okay, so the task is really trying to determine what those conformal blocks actually are. And so this basically thanks to, I think this really initiated in a series of beautiful work by Dolan and Osborne, and I think before the advent of all this conformal bootstrapping was really kind of esoteric study that only a very small group of people are familiar with, but happily they find the use in the recent years. But anyway, so we can actually, basically the punchline here is that those conformal blocks actually satisfy a set of partial differential equation, and they are basically goes by the name of, they come from this so-called quadratic Kashmir operator. And it's most easy to write them down instead of consider the d-dimensional conformal field theory, but trying to embed it in the d+2 dimensional space. Then you can realize the conformal symmetry transformation as a Lorentz transformation in a d+2 dimension. And you can write down this, so L1 and L2 here are really like the Lorentz generator in this so-called embedding space. So you can construct the Kashmir by just contracting all the indices of those Lorentz generator. But I think we can rewrite them in terms of those z and z bar coordinates. And to do so, let me just define these two second order differential operator. One is z, and for z, and the other is for its conjugate z bar. Then basically the action of this quadratic Kashmir on the scalar conformal block can be expressed in terms of the following second-order partial differential operator involving z and z bar. So here you can see that the dimensionality d, which really entering as a parameter inside those equations. So you can basically determine the conformal block in the arbitrary dimension just by really trying to solve those differential equations. Essentially, the scaling dimension and the spin of the exchange operator determines your eigenvalue, and then from asymptotic behavior, you can solve for what those guys actually are. Okay. So in addition, basically to determine the form of a conformal, that was sufficient. You just have to solve for that differential equation. But in addition to those quadratic Kashmir, it turns out you can actually also form a so-called quartic Kashmir operator. Basically, just take 4 of those Laurent generator contractile indices and so on. And again, they will be expressed in terms of those differential operator dz and dz bar I defined earlier. But now what you actually have is basically 4th order basic partial differential equations. And we will see the use of those momentarily. But basically by definition, of course, they commute with each other. So I should say that delta 4 here is really what you write down when you consider the action of the C4 explicit on the scalar conformal block also. Okay, so what's the status? So basically, the explicit closed expression for the scalar conformal block are only available in even dimensional conformal field theory. And this basically was solved in a beautiful paper by Dolan Osborne in 2011. And basically, they can be captured in this combination of the hypergeometry functions. So in the 2-dimension, basically that's the case the simplest. In fact, all this cross term, so I was trying to show that basically this term vanishes. So they basically you reduce the PDE into essentially just the ODE, and you can just write down the answer straight away. This is just basically a simple hypergeometry function. And in 4-dimension, you can also solve relatively easily that this basically comes from those kind of products. And in 6-dimension, that now things get a bit more complicated. You have to start considering the linear combination of those product hypergeometric function, and there are 5 terms. So, but all this coefficient can be fixed. But however, for the general d-dimension, like for example, even if you look at the 3 dimensions, or if you want to try to going away from the integer dimensions, you basically have to rely on those iterative approach, and there are those recurrence relation which we have to introduce a new coordinate transformation, and those were done in the paper by Reichkopf, and there's also the paper by Costa et al. Now basically you get some final answer like this, where the coordinate r and theta are related to the z coordinate I introduced earlier. But basically this is a kind of recursive approach that I suffer the usual problem of the recursion relation, that you have to determine the coefficient at the leading order and the next order before you can continue, and so on and so forth. And the question I was really trying to, for example, study the modular property of those functions, it becomes rather kind of opaque and difficult question to do. So if you really want to use them. Okay, so what's the new spin? So basically this is where the kind of integrability trying to come and help us. So let me just flesh out the particular integrable system we'll be considering in this talk. So this is basically given by the following Hamiltonian. And we can basically regard this as a kind of variation of the kind of more familiar trigonometric Caligero-Southland spin system. So usually you only have the first line. So here we basically only have 2 degrees of freedom, and you only have the first line. And for the trigonometry, you basically have the sine function. But now, in addition, we also have all this basically single particle potentials. So, and this goes by the trade name of hyperbolic collinear spin chain of a type of BC2, basically coming from the fact that so you have those permutation operator, which is basically spin the degree, exchange the degree of freedom, but also this k tilde, which in addition to swapping them, but you also bring the minus sign, but you also have those reflection operator, basically flip the sign of those coordinates. So that's the integrable system we'll be looking at. And like all integrable systems that for n degree of freedom, they should possess commuting conserved charges. So for this type of, in general, for those collinear Sutherland kind of spin chain, it's most easily to express those commuting conserved charges in terms of the so-called the Dunkel operator. So for this system, these are the associate Dunkel operator. So despite the fact you can see they involve basically both a u and u bar coordinate, and they involve the first order derivatives. But basically, thanks to the presence of those reflection and permutation operators, you can really show them just easily that they actually commute with each other. And from those, you can easily construct the commuting integral motion. So in this case, there should be two, since they are 2 degrees of freedom. And one of them, of course, is a Hamiltonian. And the other guy is what I call the I4 here. OK, so now I want to establish the following exact mapping. So I guess this one should really come first. Basically, the statement here is that I want to say basically scaling conformal block is actually an eigenfunction of this hyperbolic collinear Sutherland system. But really to hammer the message home to establish this correspondence between the CFT and integrable system, you should also see all the commuting conserved charges appear on the CFT. So I will also try to show that basically all these commuting conserved charges I showed earlier are really given by those quadratic and the quartic Kashmir operators. So that's the name of the game, and the approach is actually very simple. So we basically, well, we can see that both of them, well, of course, they commute. So we basically have to find the appropriate similarity commutator preserving transformation. And basically to relate the CFT Kashmir to the commuting integral motion. So the desired transformation is actually given by the following double cover map, which essentially, so for those people who are in this game, now they notice this is basically like a radial coordinate change, but up to a minus sign. Or in a way, this is also very similar to the Joukowsky map, like Shota was talking about earlier. So that was a coordinate change you have to do. And basically now you plug in this kind of ansatz and you solve your differential, your ordinary differential equation and try to match the form with the hyperbolic collinear Sutherland. Then you'll find that this is basically the desired similarity transformation we need to have. And with this, then you can basically show that if you sandwich your this quadratic Kashmir operator in between of those two guys, then basically you can identify its action on the conformal block, which is symmetric under the U and U bar exchange. It's actually basically just given by this the hyperbolic collinear Sutherland Hamiltonian. And here you need to basically identify the parameter on the both sides. So the A here is identified with scaling dimension, and B and B prime, identified with a space-time dimension, and B and B prime are actually identified with a scaling dimension. So, and in particular, when epsilon equals 0, which is a 2-dimension, and epsilon equal to 1, which is 4-dimension, that all this pairwise interaction actually cancels, and it's kind of cute that the system actually reduced to something you did in the elementary quantum mechanics. This is something called Poisson-Taylor Hamiltonian. So, but more generally, now we have established the following correspondence that basically the eigenfunction of this hyperbolic collinear Sutherland is basically mapped to the conformal block. And one good news about this is that, okay, now what? So basically it's that the eigenfunction of this class of integrable system has actually been solved and studied to some detail by the mathematician, namely by Kuhlweider and people like Eric Rains at Caltech and the collaborators. So we can now basically obtain the exact form of the scalar conformal block for arbitrary d dimension, and they are given by something called a virtual Kuhlweider polynomial, as named by Eric Rains. This might look quite intimidating, but the point is that those things in the Q go to one limit actually has an expansion in terms of Geigenbauer polynomial. So you can really match with, for example, the radial expansion people have earlier. And for general Q, they can also, I will be done. They will be expressed in terms of those Madonna polynomial and so on. And they are labeled by kind of two-row partition associated with the scaling dimension and the spin of the exchange guy. But at that point, you might thought, well, this might just still be some kind of mathematical coincidence. So now I want to basically show that you can also really establish all these community conserved charges. So what you need to do is basically trying to express also the quartic Kashmir in terms of the I2 and I4. And as we reviewed earlier, this was a complicated fourth-order differential operator, but we can break it down a little bit. So we consider some building block for it. There was some combination like this. But this can be actually related to the following combination of the Dunkel operator, basically when you set the dimension to 2. And so now we can define the following combination Dunkel and the permutation operator. Then you can show that basically their action on the eigenfunction is actually given by the basically now if you sandwich those things in this function T epsilon, which is basically a difference of those chi similarity transformation between general dimension and the 2-dimension. So this guy. So now we have basically used the invariance of this function on the reflection permutation. But now crucially, what you notice is that despite the fact that this combination is actually symmetric under the under the reflection operator, but they are actually antisymmetric under the two permutation operator introduced. And those are crucial to get the power of those factor TZZ bar to be corrected. And so once we notice that and you do the algebra, then you can easily see that this thing is precisely equal to the transform. Basically now it's equal to the quartic Kashmir sandwich between those chi function. And once you expand it out, then you can see that this really expressed in terms of the I4 and also I2. But since I2 commute with I2 is trivial, then we have established the correspondence that the commuting quadratic Kashmir is really the commuting conserved charges. So one slide on generalization. So this structure, so far we have been talking about non-SUSY case. And this structure, well, this integrable system appears to be rather general. In fact, for the case of a superconformal field theory in 2, 3, 4 dimension and with 4 supercharges, recently the corresponding quadratic Kashmir has been written down, but it takes a very, very similar form as the non-SUSY guy. And I guess this really, so this basically allows us just regard this as one of the similarity transformation we had earlier. So you naturally see this hyperbolic Collet-Jordan-Sutherland emerges. But this really kind of hinges on the fact that there's this beautiful recurrence relation that those scalar conformal block really possess. And moreover, now we can also view this whole problem of determining the conformal block even in the different setup with the spin, really as kind of quantum mechanical problem. So basically now we have this set of eigenfunction for the hyperbolic Collet-Jordan. Then now we know its orthogonality and so on and so forth. Then we can try. They really serve as kind of a natural basis for you to expand all the other the conformal block. For example, the cases with a spin, really just as a linear expansion of all these guys. And we did some explicit example looking at the case of the 4D. Recently, there's a couple of beautiful papers by Italian groups study those 4D conformal block, but with the spins, and we try to expand their answers. Okay, that's my conclusion. So this is really just a beginning of a series of studies. And so there are a few obvious directions to go. First is that, okay, we are looking at the 4-point function, and this is related to, two-particle color-George-Sutherland. And the natural questions are, okay, do higher point correlation function also have this underlying correspondence with quantum integrable system with a more particle inserted, for example? And also, so far, we really consider this kind of global conformal symmetry or conformal block. And so can this correspondence with the quantum integrable system also extend it to, the Virasoro or the WN conformal block in two-dimensional CFT beyond what have people study, involving those degenerative vertex operators? And finally, I think given the recent development, people know how to calculate all this conformal block using the holographic method, namely by the UCLA and also the group by Kaplan and Fitzpatrick and so on. Is the connection with integrable system accidental? Basically, we want to understand, where do those integrable systems really come from? That's really a question. And I think the answer is that they should probably lie in on this first trying to realize those things in the holography side, which has been done, and then try to see whether we can actually see those integrable system emerges on the gravity side. And I think this is a natural thing to go, right? Basically, in the old days of integrability in ADS-CFT, we studied the scaling dimension, or basically two-dimensional, basically a two-point function. And then Shota talked about the development 3-point function. And then there's a 4-point function. There's an earlier story of Elder and Modesena related to minimal surface and so on and so forth. But what about the building block of those 4-point function, namely the conformal block? Could there be some integrable structure out there for us to explore? So I will end my talk here. Thank you. Okay. That's essentially, yeah. I think, yeah, that's right.
My question is that is any two-degree system with two-degree freedom integrable? Naively, I would expect there's a charge of momentum, then there's energy control. So my concern is that how strong is an indication that this would be generalized to the, for example, higher degree freedoms?
Oh, you mean like a high point correlation functions and so on. Yeah, the first things I think, the way I think about it is slightly different. Basically now when you decompose the high, for example, if you want to decompose a higher point function using the OPE, then usually it actually becomes some kind of sums, right? And now, so what I'm trying to say, basically now you have to identify, you have to see whether those things can actually be diagonalized and turn into some new eigen function, and then of some differential operators. And then you want to see if among those differential operators you obtain can be related to some integrable systems and so on. So yeah, that's something we are not 100% sure right now. But on the other hand, I think on the gravity side, that there are indications. So this is very sketchy, and this is purely speculation right now. Is that so? In the approach by the Krause et al., so what they studied was those so-called geodesic Witten diagrams. And basically, we first want to consider some kind of semi-classical configuration, like in the integrable literature. So the natural parameter to take large is something like scaling dimension of those external operators. You may think this will wash away all the information, but the thing is that the conformal block actually depends on only the differences between all these external guys. So you can take, for example, delta 1, delta 2 to be large, but delta 1 minus 2 to be fixed. And then now you basically have a very heavy object, and this is looking something like a spinning strings inside the ADS. And then you can try, then the two sides you do that. Then they exchange some line degree of freedoms. And then you can try to build a higher point function, like from this kind of picture. And I don't know if this will actually really demonstrate that the integrability naturally, this kind of integrable system I saw here naturally emerges. But I still living, in some kind of hope that maybe even at the leading order, there's some analog of minimal surfaces or spinning string kind of picture will appear. Then there might be something there. And the oldest worry about, different different decomposition channel, different those things may actually get washed away in this limit, become subleading correction. But that's just my speculation.
Okay, if there is a short question, we could take it.
Yeah.
No? Okay, then let's start with Heng again.
Yeah.
And also the whole other people.
Yeah.